but science explains the origins of the universe within the Big Bang Theory. According to this theory, the universe arose from the explosion of a singularity, a point where conventional laws of physics break down. The singularity is a point in the fabric of space and time where the concentration of energy and matter becomes extraordinarily high, reaching almost an infinite level, while the spatial and temporal dimensions are reduced to near-zero values. This model provides a framework for understanding the initial conditions of the universe. However, recently, the James Webb Telescope has made a bold announcement that the universe has existed uninterrupted and that the Big Bang Theory is wrong in its approach. If you're interested in keeping up to date with news from the universe and its surroundings, subscribe to our channel, hit the like button, and turn on the notification bell to never miss an update. The concept of singularity describes a state where neither time, space, nor matter existed in a form we understand. The question that arises is where the singularity came from, what preceded it, and what even triggered the event that culminated in the Big Bang. The nature of this primordial state is still a matter of deep investigation and theoretical exploration. It is debated whether the universe has existed eternally or whether it had a definite starting point. The singularity that preceded the Big Bang event contained the entire mass present in the universe, resulting in the complete suspension of the flow of time. This aligns with a perspective proposed by Albert Einstein, who suggested that traditional notions of time and space may not apply in such extreme conditions. Some suggest that debating what happened before the Big Bang is meaningless since the concept of before had no place in this context. The idea that the universe is not expanding in empty space may be difficult to conceive, as it challenges our everyday understanding of space and motion. This conception is based on a theory known as the Einstein theory of general relativity, which he developed in 1915 and which remains to this day our best description of space and time. This theory provides a comprehensive framework for understanding how gravity operates and affects the structure of the universe. The theory of general relativity is supported by evidence such as the expansion of the universe, which was discovered by American astronomer Edwin Hubble in 1929, revolutionizing our understanding of cosmic dynamics. In addition, there is the cosmic microwave background radiation, which is uniformly distributed throughout the universe and was discovered by American scientists Arno Penzias and Robert Wilson in 1965. These discoveries support the basis of our current understanding of the evolution and nature of the cosmos and provide a snapshot of the universe's infancy. This radiation emerged approximately 379,000 years after the Big Bang in a period known as the hydrogen recombination era, marking a key phase in the universe's development. According to the Big Bang Theory, in its earliest moments, our universe was tiny, no bigger than an atom, and extremely dense. In times past, the notion of nothingness was a sustainable state, and the universe existed in a form that defies our typical understanding. Asking how long it lasted is irrelevant since, during this period, the concept of time simply had no existence. In this era, our world emerged from a random quantum fluctuation that emerged from the void, representing a significant level of depth and complexity. Perhaps a question of very relevant might be whether this quantum fluctuation was truly random. As Einstein famously put it in his phrase, "God does not play dice with the universe," suggesting a deterministic view of fundamental events. With this notion in mind, it is interesting to reflect on the implications of this. What prevents another small fragment of energy-filled void from appearing again, leading to a new Big Bang? There is a possibility of this occurring without 100% probability, which could annul the existence of mankind and challenge our understanding of cosmic events. In the multiverse theory, the emergence of life occurs through a natural phenomenon in which universes with parameters conducive to more black holes will have a greater chance of generating offspring, thus increasing the probability of life being present in those universes. This idea proposes that our universe might be one of many, each with different physical constants and laws. Recently, renowned physicist Brian Cox explored the fundamental question of how the universe began. Cox presented the Big Bang theory but challenged the conventional perspective by introducing a fascinating approach: the idea of the existence of a time before the Big Bang. This intriguing notion expands our understanding of the origins of the universe and opens up new avenues for exploration. The notion of a pre-Big Bang universe connects to the theory of cosmic inflation. According to this theory, the universe underwent an exponential expansion in an extremely short period after the Big Bang, a process that helped shape the large-scale structure of the cosmos. This significant growth allowed the universe to become uniform, explaining its observed homogeneity on a large scale. Although inflation remains a fundamental part of the prevailing cosmological model, Cox's idea of a pre-Big Bang state adds a layer of complexity to the chronology of the evolution of the universe, suggesting a richer and more nuanced history. One question that arises is what could have caused this primordial energy to trigger such a sequence of events? Could it be the result of interactions between forces that we do not yet fully understand? The origin of such events remains one of the biggest mysteries in cosmology. Cox's ideas about the time before the Big Bang are supported in the work of Roger Penrose, an outstanding mathematician and physicist who was awarded the Nobel Prize in Physics for his contributions to the understanding of black holes. Penrose's work has been instrumental in expanding our knowledge of the universe's fundamental aspects. Although his focus is on black holes, Penrose also introduces the concept of eons, which occur in a cyclic framework. Each aeon begins with a Big Bang, followed by a period of expansion, contraction, and finally a big crunch, in which the universe returns to its original state. This cyclic cycle sets the basis for a new aeon, perpetuating itself indefinitely and offering a unique perspective on the universe's lifespan. Penrose's aeon theory revolves around black holes, celestial objects of enormous gravitational force that emerge from the collapse of massive stars. Over time, these black holes evaporate through Hawking radiation, releasing energy. Penrose speculated that dead black holes from earlier eons may still exist today, leaving possible imprints in our observable universe. These remnants Penrose called Hawking points, in honor of Stephen Hawking and his contribution to the understanding of Hawking radiation. The late physicist Stephen Hawking's proposal could offer clues supporting the existence of states prior to the Big Bang. Hawking's theories have been pivotal in advancing our understanding of black holes and the early universe. Penrose's idea of Hawking points could represent a potential clue to the existence of a pre-Big Bang universe. These enigmatic points, which are about 8 times the size of the Moon, refer to slightly warmer areas in the sky that can be detected by advanced observational techniques. While Hawking's concept of the dots stands out in the scientific conversation and highlights the fluidity of our understanding of the beginnings of the universe, the discussion also highlights the importance of scientific exploration and the potential for paradigm-shifting discoveries in the future. The exploration of these ideas underscores the dynamic nature of scientific inquiry and the ongoing quest to uncover the universe's deepest mysteries. As with any revolutionary scientific proposal, Brian Cox and Roger Penrose's exploration of a time before the Big Bang faces challenges and controversy. Critics argue that the concept of a pre-Big Bang universe remains speculative as it lacks direct observational evidence, making it difficult to test or verify. In addition, the cyclic nature of Penrose's aeon theory raises questions about the conservation of energy and the ultimate fate of the universe. Some skeptics question the feasibility of an infinite cycle of eons, as this could conflict with the laws of thermodynamics and other fundamental principles of physics. These debates highlight the complexities and limitations of our current understanding, driving further research and discussion in the scientific community. Now let's delve into another related theory, the multiverse hypothesis in cosmology. This notion suggests the existence of multiple universes, each with its own physical laws, constants, and properties, potentially leading to a vast and diverse multiverse. The basis of this idea lies in the belief that our universe could be one among many in a vast and diverse multiverse where different regions of spacetime might have different fundamental constants. The concept of the multiverse has gained momentum as a way to explain certain aspects of our universe that seem to be finely tuned for the existence of life. Scientists have observed that the fundamental constants and physical laws governing our universe appear to be carefully balanced to allow the emergence of life as we know it. From this observation, some have proposed the anthropic principle, which holds that our universe has the characteristics it does because it must be capable of hosting intelligent observers like us. This principle suggests that the fine-tuning we observe is not necessarily a coincidence but a reflection of the universe's requirement to support life. The multiverse hypothesis proposes that our universe is not unique but rather part of a vast ensemble of universes, each with its own distinct properties and laws of physics. This idea extends beyond the standard Big Bang model, suggesting that multiple, possibly infinite, universes exist with varying characteristics. Some models posit that these universes are spawned from different regions of a larger multiversal structure or from quantum fluctuations in a higher dimensional space. This theoretical framework is rooted in the idea that our universe's specific conditions, which seem finely tuned for life, might not be as special as previously thought, but rather one instance among many possible configurations. This hypothesis is informed by several scientific theories. For example, the concept of cosmic inflation, a rapid expansion of space in the early universe, may not only explain the uniformity of our observable universe but also suggest mechanisms for generating multiple universes. According to some inflationary models, different regions of space might undergo separate inflationary events, leading to the creation of bubble universes with varying physical laws. Each of these bubbles would represent a distinct universe within the multiverse, with its own set of constants and properties. Another relevant theory is string theory, which posits that the fundamental building blocks of the universe are not point particles, but rather one-dimensional strings vibrating at different frequencies. String theory allows for the existence of multiple dimensions beyond the familiar three of space and one of time. The different vibrational states of these strings can result in various fundamental particles and forces, suggesting that different regions of higher dimensional space might give rise to distinct universes with unique characteristics. This framework also introduces the concept of branes, multidimensional objects that could host separate universes in higher dimensional space. The anthropic principle, often discussed in the context of the multiverse hypothesis, addresses the apparent fine-tuning of our universe's physical constants. This principle suggests that the properties of our universe are compatible with the existence of life simply because if they weren't, we wouldn't be here to observe them. From this perspective, the fine-tuning observed might be a selection effect in a multiverse scenario, where only universes with conditions suitable for life are capable of producing observers like us. The idea of a multiverse also intersects with quantum mechanics, particularly the many-worlds interpretation. According to this interpretation, every quantum event results in a branching of the universe into multiple, non-interacting parallel realities. This implies that every possible outcome of a quantum event actually occurs in some branch of the multiverse. While this interpretation remains controversial, it provides a framework for understanding the vast number of potential outcomes and realities that could exist. Observational evidence for the multiverse hypothesis is challenging to obtain. Direct detection of other universes is inherently difficult because they might be completely disconnected from our own observable universe. However, some scientists explore indirect evidence through the study of cosmic background radiation, the distribution of galaxies, and the search for anomalies that might suggest interactions with other universes. For example, some researchers have looked for signs of collisions between our universe and other bubble universes in the cosmic microwave background. The idea of the multiverse also raises philosophical and scientific questions about the nature of reality and our place within it. If multiple universes exist, what implications does this have for our understanding of fundamental concepts such as causality, existence, and the nature of scientific laws? The multiverse hypothesis challenges our traditional notions of uniqueness and determinism, suggesting that our universe is one of many possible configurations in a vast and diverse cosmic landscape. The exploration of the multiverse hypothesis also intersects with discussions about the ultimate fate of our universe. Some theories propose that our universe might eventually undergo a big crunch, a collapse back into a singularity, or it could continue expanding indefinitely. In a multiverse context, the fate of our universe might be just one possible outcome among many, influenced by the properties and interactions of other universes in the multiverse. Furthermore, the notion of a multiverse raises intriguing questions about the nature of laws and constants in physics. If universes within the multiverse have different laws of physics, what determines these laws, and how do they relate to the fundamental principles governing our universe? This exploration could lead to a deeper understanding of why certain constants and forces have the values they do and whether these values are arbitrary or a result of deeper, underlying principles. In summary, the multiverse hypothesis offers a compelling framework for addressing questions about the fine-tuning of our universe, the nature of cosmic expansion, and the fundamental principles of physics. While still speculative and challenging to test directly, it encourages ongoing exploration and debate in both theoretical and observational cosmology. As research advances, the multiverse concept might reveal new insights into the fundamental nature of reality and the diverse possibilities within the cosmos.